Okay, thank you very much. Just before I start, maybe I can just give you a little bit of context. So my name is Anne-Marlène Rüede. I'm a PhD student at eSpace, and my background is in architecture and space technologies. So I work a lot with high performance design. And so I'm currently in my first year, which means that what I'm going to present is actually closer to a project proposal for the work I'd like to do in the coming years, rather than a finished project. So any comments or input are very much welcome. So I'll start sharing. Okay, so I'll talk a little bit about generating sustainable space mission concepts by reusing robust design patterns. So first of all, again, a little bit of context. Actually, Professor Kokiho explained this very nicely in his talk just before. Up until now, a lot of the missions that we had were mostly simple mode missions. So these are satellites, rovers, space probes, for example. They are sortie style missions. A few notable exceptions are our space stations, are the Hubble Space Telescope, or the Apollo missions. Now, in the future, complex mode missions are expected to become a lot more common. And complex mode missions are those that rely on on-orbit servicing, and they're necessary also for debris mitigation, for enabling human exploration missions, and also enable shared services, which will be critically important in the upcoming lunar, cis-lunar economy. So the problems that we have identified with these complex mode missions is that the generation of complex mode mission concepts is quite difficult. Furthermore, my apologies, the identification of potential synergies between different missions is also difficult. And finally, same for the identification of missions likely to benefit from a particular infrastructure. So I'll go a little bit more into detail about this. But one thing that we can see is that these three difficulties that we have identified fundamentally are a difficulty of mapping between function, form, and routing. So I'll just dive a little bit into the Apollo example. So the Apollo example first started with the idea of a direct mission, and mostly this consumed too much fuel. And so the two questions were added, and these two questions are, is there going to be an Earth orbit rendezvous, and is there going to be a lunar orbit rendezvous? And what we can see when we look a little bit more into detail regarding these mission concepts is that here with the direct missions, we're actually not very close in terms of proposed concepts to the utopia point in this Pareto chart. And once we add, actually the really important question to add was the lunar orbit rendezvous question. And this was a lot closer to the utopia point and was subsequently selected as being the Apollo mission concept. So what we see here is that it's really critically important to find these right questions. And finding these actually took over a year, 1 million man hours. And the response came from one man who had difficulty having to be heard. So we really have to find a more methodical way to be sure to raise these right questions when we design mission concepts. So what we propose is to develop support, decision support for generating options, identifying high-value candidates, and furthermore, communicating and visualization around the generated options. So I'll go a little bit about into pattern languages. So I'll explain quickly what pattern languages are. We propose to use this method, and four of the advantages that this method has, I'll explain just after how it works exactly, is that it's extremely adapted in high-performance design problems. It is what's called a trawling method. So trawling is really kind of casting a net into the trade space of options and pulling out the options that are the most suitable, but not only the ones that we probably know are suitable, but it also does generating the unimaginable. So it also picks up options that we would probably never have really thought about. And finally, it's quite computationally efficient. So I'll make a little detour into architecture to explain the concept of pattern languages. So in 1969, an architect, Christopher Alexander, was tasked with designing 1,500 houses for low-income families in Peru. But the problem was that all of these families, they have different requirements, they have different needs, number of children, for example, and they have different budgets also. So a one-size-fits-all solution would not have been adapted. And yet, if we would have drawn every house separately, just the billing cost of drawing each house would have by default made these houses inaccessible for the target population. So he came up with a system, which is a pattern language, which enables to automatically generate feasible options for each family. So the way that this works is that each family received a question in which it was the families were able to voice their preferences. So, for example, this is the first question. What size of sala would you like to have? You can have a tiny sala with option for medium sala later, medium sala, large sala, and they all come with different costs. So depending on each question, families were able to verify that the costs correspond exactly to what they had wanted to spend on the house. And interestingly also, what we can see is that here we have option for medium sala later. So this is really also an opportunity. This is the right level where we can include solutions for later evolution and flexibility and robust design. So after the families responded to the questionnaire, draftsmen would, within 1 hour, just follow a simple algorithm. And depending on the responses in the different questions, they would add or not add certain elements which were pre-drawn, which are these patterns. And together, they would then exactly give a feasible solution which corresponded exactly to the needs of the family and was exactly within the budget. So how it works is that there's a budget with key criteria that are decided upon. In this case, it was a monetary budget, but it does not have to. There are patterns. These patterns are essentially known and reusable solutions which have a positive or tend to have a positive impact on the key criteria. And they are also defined in terms of form, function, and routing constraints. And finally, we have an algorithm which generates phrases. So these phrases are the complete options that are feasible and also compiles the budget with the key criteria. So taking all of this and translating this for space mission design, what we find is that we can have these patterns or shapes for routing and additional information such as color and additional layers for changes in mass, for example, and together they produce solutions which are known to have a positive impact on mass and cost, for example. These are quite common criteria, but it doesn't have to be these only criteria. And then we find solutions such as prepositioning, for example, in situ resource utilization, in situ remanufacturing, shared storage, stage separation, deorbiting, in situ refueling. So these are all strategies that have also been mentioned in other talks and which are known to have a positive effect. So the way this works is that if we take a pattern example, such as separating a stage, it is described It's described in terms of its impact on form, function, routing, on the key criteria. It calls other patterns also. And there's also additional information. So for example, in this case, we could say that there is creation of space debris if this pattern is run. And this is something that we might want to take into consideration when making a choice. And so with these different patterns, we are actually able to reassemble the concept of space missions. So this is the Apollo example. And just to explain a little bit the way that these work more into detail is, if we look at the concept of circular economy, which is quite a central concept in sustainability, there are these strategies which are reduce, reuse, repair, recycle, recover, and dispose, and these are preferentially used. Now, we can apply this into the patterns and say, for example, if we run a departure pattern. So let's say we depart from the moon, for example, then the first question that would be raised is it possible to leave something in place? If yes, then is it possible to reuse whatever we have left in place? If yes, then can we assemble it with something else? And if so, this would recommend using modular design. If it cannot be assembled, it would recommend using it for spare parts and then using design for in situ reparation. And actually, this is exactly what happened with the Apollo mission. For example, the rovers were left for spare parts. And then the next pattern runs. So what we are looking to do is to have an input, which is mission objectives from the user. And these are translated into constraint patterns that we know have to exist. So if we have the Apollo mission, for example, we know there's going to be a launch. We know there's going to be an arrival on the moon. And because it's a human mission and humans are supposed to return on the Earth, we know that there's another departure from the moon and another arrival on Earth. So these are our constraints. But then within, between the different patterns, we can then have an algorithm that runs and actually develops these patterns based on what was shown just above. So these options would actually develop on their own. And interestingly, what we see with these is these questions that were raised by John Houbolt, the Houbolt questions, which included the lunar orbit rendezvous. They actually appear naturally in the patterns. So the choice of using or not using a pattern at one specific location is actually a direct translation of these decisions or questions that are raised. So in that sense, this system actually raises these questions. So we do see here this pattern actually is equivalent to a lunar orbit rendezvous. And as mentioned, every time we run through the compiler through the patterns, there is information that then compiles and can be added. And when we run through the Apollo example, actually we find the information which, for example, for the design of the infrastructure suggests already the constraints that give exactly the design that was used. So now I showed the Apollo mission example, but this could be used for other missions. Here, example of human Mars settlements or constellation servicer, multiple spacecraft servicer, for example. And again, this is in the Apollo example. What it does is, first of all, generation of mission concepts. So up here you can see the four main concepts which were considered. The compiler calculates, in this case, we have chosen as key criteria risk and mass to LEO, but this does not have to be the case. We can also consider other key criteria. So it compiles risk based on this pattern structure. And it also compiles the propellant required exactly based on this pattern structure. And then we find, so this is proof of concept that we did, and we actually find results that they're simplified, but they correspond with the historical results, and they do follow the structure of the patterns. So what it allows to do is to identify sets of high-value mission concepts that merit further investigation. So this does not optimize a mission concept, but rather it generates and then shows which mission concepts are likely to merit further investigation. And what it also does is, in terms of communication, so it creates these, it automatically creates these different diagrams, which are very comparable because they have a very standardized structure. So it helps with the graphic understanding and comparison of mission concepts, and also it explicitly mentions the design constraints, recommendations, and opportunity that could be made explicit. An example was the stage number in order of Apollo 11 infrastructure components. This could be when to reuse material, modular design, when to leave behind for spare parts, for example. And in terms of outcome, the type of question that we think could be answered with such a system would be, what are good candidate concepts for a given set of mission objectives? So that's the first type of question. But then, because when designing these missions and also when designing infrastructure, they're increasingly interconnected, we are also looking at what are infrastructures that could be shared between multiple missions with given sets of high-value objectives, or given a specific infrastructure design, for which set of mission objectives could it be the most useful? So essentially, it's kind of reverse engineering itself. So this is the project proposal that we're currently developing. So thank you very much for your attention. Please put any questions in the chat, and any comments are absolutely welcome and would help me a lot. So thank you very much.